given the capital D is the power of x with the exponent c, depending on the c value. Then the results could be like this. If C is less than 1/4, then in this situation, the arrow term can be effectively bounded, efficiently bounded, sorry. Is small in comparison with the major term. The order is just, I'm not going to say, by the so-called Bombiri Vinogradov theory. But T2 star is less than T1 star. We are able to evaluate both these two sums. Yeah, S1 is simpler, so even I didn't write down the arrow terms here. It should be very simple. But S2, the arrow term is complicated. In order, we are able to handle the arrow term. If we take C is less than the 1/4, we can handle this. We don't worry about this. But now this coefficient is smaller than that. We wish to prove S2 is greater than S1, but we couldn't. Now, on the opposite situation, if C exactly equal to 1/4 is almost the same as this situation. I'm not going to say. Say C is equal to 1/4. That is in my paper, like this. Then, in comparison, if we compare the main terms, the coefficient in S2 star this is larger, but this is smaller. But we need to choose the L. That's a minor problem. Then T2 star is greater than T1 star. So if we just compare the main terms, it's good enough. But till now, one is unable to show that the arrow is small in comparison with the main term. Let me say, we have solved the bounded gaps problem, but still in general, we are unable to show this is small. And to show this arrow term is small, what I can say is, even we assume some very strong hypotheses, like the generalized Riemann hypothesis, still we are unable to show this. So this is the very deep problem. Also, we say, as mentioned, we say the gap, the difference is only within the hair breadth, but this is less than 1/4 or greater than, slightly greater than 1/4. But that's a big difference. We're unable to handle the arrow term. Then, what I like to say is, on my paper, I say I just give two observations. One thing is like this. we say observation, observation 1. We just say in the expression for the number n, we just say, we assume, we impose and constrain, or we just say, we just assume the variable d has only small prime vectors. That is, we say, let me use this p. That's the different from the polynomial p capital P. P is equal to, say, equal to prime of the p, which is less than a very small power of x. Similar like this. So in other words, we just assume we redefine the number n is equal to everything the same as that d dividing capital P n, and the d is less than capital D. Now also, we impose an extra constraint. That means for each such a d, the largest prime factor of such a d is less than this power of x. So it is a small power of x, then everything else is the same. And we choose a suitable L. Here I may not to say something more. We have this one. Then in this way, still, oh, yeah, so, thank you, I forgot. This is the constant factor. To make it to normalize the form. Still, if we just impose such a constraint, then we just recount, re-evaluating the S1, S2, we get something. Still, if we just consider the major term, the coefficients of the major terms, still is S2 is larger, S1 is smaller. But now, more importantly, we say the observation 2. That's a crucial part. Still like this, we impose and constraint on the coefficients, or actually on the d. So we just consider the d. The d has only small prime factors. That is, we say with the constraint D imposed, then the resulting arrow, we say the E star, can be efficiently bounded. Then, still like this, we choose the C equal to the 1/4 plus the reciprocal of 1168, slightly greater than 1/4. Then we impose the constraint here. The resulting arrow can be efficiently bounded. Therefore, we can prove the bounded gaps between primes. Here, what I like to say is that should be a long story. That was the formal works. The work were due to Bambiri, Friedland, and Uranich about the bounding the arrow terms. Their work was earlier than the Goldstone Pinch and how to pronounce it, Yodim maybe. They are concerned to estimate the error in the distribution of primes in certain arithmetic progressions. But they, just like here, we say that D is equal to, capital D is equal to the x raised to 1/4. If we take the capital D squared, it is x to the square root of x. They tried to say, to estimate here we say that also we say, but here this D could be like the D squared earlier, but I just put it here. The number, let me say n is say, similar to x or less than x, that doesn't matter. This is the bounded function. But n is congruent to C mod D. This constraint almost is useless. Here the number the n is equal to the moment function. Let me just, essentially it's the natural log of if n is a certain power of p, say p raised to p greater than or equal to 1. Then we say here we have a capital D. This corresponds to the square of capital D in our situation. But I'm not going to say something more about this. So if D x is equal to the power of c still. C is less than 1/2. Maybe C is just equal to 1/2 or very close to 1/2. This has been done by the Bambiri-Binek-Dragov theorem. It's solved. But if C is even it is very slightly greater than 1/2, that they call it the sort of a stronger version of Pompeo-Vinogradov theory. But it is very in general. Still now it is unsolved. We know no one can solve it. Although there are very strong conjecture like the C equal to 1 minus epsilon. That helps them. I can't pronounce the name very precisely. Other conjecture. In this case, they got a certain very significant results, but in general, they couldn't put the absolute value in the sum. So still, it may not apply to our problem directly. But here we say we impose the condition D dividing here, although this D is slightly different than D. But if the C in my way is like this, if C is greater than 1/2, that is a double of this number. And if we make a constraint, which is the D dividing the smaller p like this p is the same as that, then we can bound it with this sum. We only need this constraint, but in our question, this is no problem. That never change. Essentially, that never change the main terms. The main terms is still the S2 is greater than S3. But this implies, we may try, say, if D approximately has the order like the square root of X, but every prime factor of D is less than a very small power of X, then D could be written as the factorization in mind. Then for the RU, we can arbitrarily, we have a very flexible choices for the range of R. Then in our estimation, that make more and more variables. The maximum number of the variables, we have the summation over 10 variables or something like this. But they give us more space, more room to make safe. Eventually, we achieve the estimation and prove this one. So this is mainly what I can say. It's like here. Any question? Any question? What's the bounds? Actually, let me say, first I say we can bound this. I say this is a secret. First I mention this, then I will say something about the exponential bounds. If we use the Vinogradov notation, maybe it's different. Maybe at most we have the power of this one, right? But we can prove sigma is equal to the O. We just say a power of the natural log, which is K is a large constant. Actually, it could be arbitrarily large. We need to prove this. Then the process of reducing the sums to estimate a certain, that should be a long process. But what I can say is, reduced to one thing is the so-called Grossman sum. That is the sum. We just use the algebraic notation. It is, we say it is C mod D, but it's a reduced summation. This is the code here. Let me say something. Let me say something. We say whenever C is co-prime to D, then we say the C bar is the solution such that C is just a multiplicative inverse. C bar multiplied by C. Then here, for this one, we use the weights bound. Still now, I mean, yeah. It helps us to save a square root of essentially from the trivial estimate. And the last, sorry. The last one I just mentioned, the deepest result used in the proof. It could be, say, a multiple Klosterman sum. That's a so-called Birch-Barbieri result. It is a consequence of the Weiss conjecture proved by Deligne. That should be in the surface case. Yeah, also it is a multiple similar to that, but there are more variables, something like still it saves the square root from the trivial estimate, like this. Anything else?
Other questions?
So usually the intermediate pairs of prime to the boundary direction seven. How often is the pair?
We actually, our method contains a lower bound of about how many pairs less than x. But this comes from, if we use the Cauchy-Schwarz inequality, it's easy to get it. But it may not be very good.
What's the other problem?
It should be using Cauchy-Schwarz. We say the number of the pairs of with edge P1, P2, they are Pi less than x and P1 minus P2. Of course, it should be greater than 0. We say less than. It is greater than or equal to a constant c times x times a negative power of the logarithm. We say it is b. Using Cauchy-Schwarz, but this b could be very large. But Cauchy-Schwarz is not difficult to get.